I think the rest of my body is used to the very small time change from San Francisco, but for some reason my throat isn't, so just bear with me. Hello, everybody. I'm really excited to be talking about this. This is a subject that I've been looking into further and further, and as I was saying to someone just outside, it feels a little bit like where there's a little piece of string and you pull on it, and you're like, oh, I'm going to get to the end of this thing in a minute, and then I'll have my talk all together, and I'll understand it, and it'll be clear. And then you're like, okay, there's more string here, okay. Like, oh my God, where does this end? So I'm really excited that I've had the chance to sort of think about this, and I hope this makes it a bit clearer. So I'm talking today about protocols with associated types and how they got that way, maybe, because we can't be exactly sure. Now, protocols with associated types. Like, why is this an interesting one to get into? I think first reason is that they seem to cause a lot of pain. If you look at what you see on the internet, you see a lot of reactions a bit like this. Like, yes, I'm using value types. I'm using Swift. This is awesome. Oh, I can't subclass. No problem. Okay, I'm using protocols, the Swift protocols. All right, I need to implement Equatable because, equality, it comes up a lot. And then, bam, right away, you get this error. Protocol, whatever you're working with, can only be used as a generic constraint because it has self or associated type requirements. You hit this, and this is what you hit as soon as you're working with a protocol with associated types. And at first, you see this, and you're like, what? Like, what does this mean? Why is this happening? Is there a quick fix? Is there a way I can go in and fix it quickly? There's not. This is something that comes up and often requires you to radically restructure your code, in that you're not going to be using protocols in the way you thought you were using them. What it's saying is you can only use it as a generic constraint, which basically means you can't use them for variables, right? And that's confusing because normal protocols work something like this. This is kind of what we were all taught in OOP school, right? You got your protocol, and then you have your type. Here it's a struct, but it could be, a class, whatever. And then you can define a variable, proto-var, which has the type of the protocol, right? And now when I'm creating an instance of my struct or my class, whatever, foo, because it because it adopts that protocol, I can assign it into the protocol. That's great. And then in downstream code, I know that I'm working with something that's a my proto. I can forget what it originally was. Maybe someone handed it to me, and all I know is that it's a my proto, so I know what its interface is, and I can call methods on it. No problem, right? But in protocols with associated types or with associated pain, that's not what happens. As soon as you have a protocol with an associated type, which you're going to have as soon as you add a type alias declaration inside the protocol definition, things are going to work differently. The type alias declaration is declaring a requirement. Every adoption of this protocol needs to say what that type alias means. So here's an adoption of the protocol for my struct foo. I'm saying foo is adopting the protocol my proto, and for its adoption of my proto, my associated type, let's say it's integers, meaning requirement. And now, when I try to write that code at the bottom, which is probably the kind of code that I used to write for protocols every day of my life, you get that error. Now, oftentimes people aren't going to encounter this first when they are adding a associated type explicitly. As I mentioned, usually the first place people run into this, at least the first place I did, is when you're doing anything that has equality. So what's the connection there? I'm not 100% sure of this, but my understanding from staring at this for a long time is that basically anytime you use self with a capital S, self is kind of like a built-in associated type. It's sort of a special associated type that's predefined to be spelled self, and whenever you're adopting a protocol that uses self, it's predefined that the adopting type is equal to the self alias or the self type name. So, if we were defining Equatable for ourselves, it would be a bit something like this. You'd have something myself, and the adopting type would have to be the one set equal to myself, and that's exactly the situation we had before. That's why I think that error covers those two cases. You're using self or you're using an associated type. The reason those things go together is because every time, the self is actually just a special case of associated types that's built in because it's a commonly needed one. And again, as soon as you say something's equatable, you can't put it in a variable. Nope, can't be done. You get an error. So that's a bit of a surprise the first time you encounter it. What does that mean? I think, first of all, it means that protocols with associated types are different enough that I suggest we stop calling them protocols with associated types. Also, my tongue is just going to wear out if I have to say that 100 times during this talk. So that's why I call them PATs. Makes them seem much more friendly and approachable. Protocol with associated type, PATs. And PATs are a bit weird. Or at least they seem that way when you first run into them. So why? Why are they like this, and what's the best way to make use of them? Is that saying that, when you understand, you forgive, right? So I wanted to understand where protocols with associated types were coming from in order to forgive them for being a bit frustrating. This is a journey in trying to understand PATs. I've got 4 questions that I want to address in this talk, and I'll feel good if I feel like I've given partial answers, at least, to all of these and made these a bit clear. So first question to think about is just, how are PATs weird? Like, let's really name exactly the ways in which they are surprising or frustrated. And then the second question is the deeper one. Why are PATs weird? Why were they made this way? Like, what's the trade-off that motivated producing these effects in order to produce some other kind of benefits? What's the point of this? Like, why are they like this? All the guys working on the Swift team, very capable guys and gals. I don't have any, I'm not saying they're making a mistake. They know more about this than I do, so I'm just trying to understand where they're coming from. The third question, is this the plan? Like, the things that are a bit frustrating about protocols with associated types, is this how it's supposed to be? Is this how it's going to be indefinitely? Or is this kind of work in progress stuff? I think that's a good one. That's a good one to understand. And then the last point is how to love them, right? How to forgive them and understand them and make the best use of them. So let's dive in. First, just to quickly review how PATs are weird. I'm going to name 3 aspects of the weirdness that I think are the key ones. So the first one, like I mentioned, is this one that they're only usable as generic constraints. Now, when you think about it, why is this weird? This rule excludes PATs from literally every single use of protocols as defined in Objective-C. Literally. And the proof of that is quite simple. Objective-C lacked constraints, right? So in Objective-C, all of the protocols you used in Objective-C, none of those were being used as generic constraints. PATs can only be used as generic constraints. There's literally no overlap. QED, right? So yeah, that's a little bit odd. They're called protocols, but literally every single protocol you ever wrote before, you could not write it with a PAT. Second weirdness. Everywhere, and so how's that expressed? The effect of this is that everywhere that you wanted to have a plain old protocol before, you wanted to have something like this delegate is defined with this protocol. Now, in order to use a PAT, you need to have a generic constraint. So now my var delegate declaration, let's suppose it's inside a class. Well, now that class needs to be a generic class. And it needs to be generic with a type parameter T with a constraint protocol. And then the delegate declaration gets the type parameter T. So everywhere that I would have had a simple kind of protocol property, I now need to have a generic context for it. And so the effect of this is that now my whole class has become a generic class, which maybe is not what I wanted. Maybe is not what I was used to. Maybe it seems like a big change just in order to be using a PAT. And the other aspect of this is that once you've done this, okay, now I'm using a PAT instead of a plain old protocol. But that little change did not get me exactly to where I was before, because now I've lost dynamic dispatch. And dynamic dispatch might have been the reason I was using a protocol to begin with. So to refresh here, if that were a plain old protocol, and I had an array of them, right, then that array of protocol objects, if it was just plain old familiar protocols, it could have had underneath a heterogeneous array of different kinds of types that were conforming to the same protocol object. And then I just go through them, and every one of them, okay, it's a protocol. I don't know what's underneath it, but I know it has this method foo, and I call foo, and then dynamic dispatch is going to do foo thing A. If it's type A, it's going to do foo thing B if it's type B. That's dynamic dispatch. That's subtype polymorphism. That's. But once you make this change so that you're using a PAT, and then you're forced to deal with a generic context, the array that you get is not an array of proto-objects. It's actually an array of whatever the type is that adopts the protocol. So you're forced into a uniform array. So you no longer have dynamic dispatch. You can no longer have a collection of delegates where all you know about them is that they all conform to the PAT. You've got a collection of delegates where they're all some single type that is obliged to conform to the PAT. So you've lost a significant language feature by making this switch to PATs. And that may have been the very feature you were depending on when you decided you wanted to use a protocol to begin with. So this only usable as a generic constraint feature is genuinely restrictive, and I think it's fair to be surprised, especially because when you look at the docs and communication from Apple, there's a lot of language that describes protocols as real types in Swift. Here in the Swift programming language book, it says, any protocol you create will become a fully fledged type for use in your code. You can use a protocol in many places where other types are allowed. Parameter type, return type, type of a constant, variable, property, type of items and arrays, dictionaries. That's actually a list of all the places that you cannot use a protocol with associated. Literally. Those are all the places you cannot use one, which is, I guess, why they have the word many in there, just to make it a bit ambiguous. In the protocol-oriented programming talk, any type you name is a first class, any type you can name is a first class citizen when he's talking about protocols. So if you find this behavior of PATs confusing, if it surprises you a bit, relax. Your brain is functioning properly. You should be confused by it, I think. Now, the third thing that's a bit weird about PATs is the way the type alias keyword works. So let me say a little bit about that. And that's actually, I think, the natural entry for diving deeper into the topic and getting a sense of where they come from and how to understand them and appreciate them and enjoy them. So type alias, there's two very distinct functions in the language right now. The first function is anytime you use the identifier type alias outside of a PAT, it's really just a syntactic convenience. It's just a way, it's like a type def. It just gives you an opportunity to create a shorter and more meaningful name for what could be a kind of long and awkward type name. I think it would be correct to say that it's not doing anything semantically. It's just a syntactic convenience. If you had a really great short-term memory, you could go through and take all the type defs and the type aliases and just pair them out and replace them with the fully specified name. It's not concealing anything or requiring anything or doing anything. It's just saving your brain from having to keep track of a longer and a kind of more opaque name. But inside a protocol with associated type, as I mentioned earlier, type alias is doing something very different. Type alias is actually establishing a semantic requirement for adopting the protocol. So it's establishing the requirement that any type that adopts this protocol needs to implicitly or explicitly specify which type is associated with this type alias. And that is interesting to think on. Type alias is, in that case, effectively defining a placeholder for an unknown type. Right? So here's a protocol animal, and every animal eats some kind of food, and let's say food's also a type. But until I know which animal adopts it, I don't know what kind of food it is. So I can say, well, there's some type called food, but I don't know yet. And whatever type wants to be an animal, it needs to have a function eat, and that function, and eat means you need to eat this food type that's your preferred food. And this is this requirements defining role of a type alias is intriguing because it sounds a bit familiar, doesn't it? You look at this and you think, well, type alias, the identifier that I name with a type alias, it feels a lot like a generic type parameter. Right? That's another case where we have syntax that specifies that we're introducing an identifier that will be a placeholder for a type that's not known yet and can be used throughout our definition. So if I were defining a struct animal that's a generic over another type parameter, I could use food as the name of that parameter, and then I could say, okay, if I produce a specialization of animal on a particular type of food, then that specialization eats that type of food. So that leads to the question, well, all these things that are odd about PATs, is that because PATs are really under the surface or conceptually best understood as generic protocols in the same way that type parameters are used for generic types? Are they really just generic protocols with a little bit of a wacky syntax? Does that explain everything? And this was the road I started going down first. No. The answer is no. They're a bit like that, but I don't think that's the most productive way to think about them. And they would be different if they actually were like that. But they are a bit like that. So it's no and yes, sort of. But asking why explains a lot and exposes, I think, probably the thinking that drove this feature. I'm speculating a bit. Let's go to question number 2, having now laid out how pats are weird. Why are they like this? So what is the problem that associated types solve? It can be used for a number of things, but I think a good way to get at it is to say that what associated types do is they solve problems where you can't represent type relationships through the tools that you have with normal object-oriented programming-based subtyping. So this is a classic example. Let's say I have a protocol food, and then grass is a kind of food. So it's adopting that protocol. And let's say I have a protocol animal, and every animal eats some kind of food. But you see, I'm not using an associated type. I'm just saying animals eat food. And now let's say I want to specify that a cow, which is a kind of animal, eats a particular kind of food, grass. If you try to do this, you get an error. And this isn't really specifically a problem with protocols. You'd see the same thing here if I defined food as a class and grass as a subclass, and animal as a class and cow as a subclass. In that case, I'd have an override there. This is not an issue with protocols. This is an issue with having only the hierarchical structure that inheritance and subclasses give you. And the error is because if you tried to do that, whether having an override for a subclass or just having it adopt for a protocol, you've violated the substitutability requirement for a subclass, right? Everything that's an animal needs to be able to eat type food. So if I create a kind of animal that doesn't eat food in general, that only eats grass, then I can't take an instance of that. I can't take a cow and just give it to you to use as an animal. Like, let's say you had a function that took an array of animals and it went through all of them and it just gave them all food objects, right? Maybe the food is, I don't know, meat, right? Well, then what if one of those animals is actually a cow and it only eats grass? Then that would fail. So it's because of this, you can't actually represent this kind of type relationship with normal object-oriented subtyping. I think the technical language for this is talking about the covariance requirements on the arguments of the methods. I don't know if that clarifies it. That's just impressive language. But with an associated type, you can be more precise. You can say every animal eats some kind of food, and when you declare that you want to be an animal, you can just specify what kind of food it is. And now it's okay. So this is a toy example, but it sort of gets at what protocols with associated types are trying to do. They're trying to provide a way for expressing they do provide a way for expressing type relationships that you can't fit into an object-oriented hierarchy. Okay, that's a bit of context, but it doesn't really explain this question of why they work quite the way they do. Specifically, it doesn't explain, well, why aren't they correctly thought of just as generic protocols? Why aren't they defined using the syntax that you'd expect from generic protocols? Because you could imagine that in some imaginary version of Swift, this is how it would work, right? You protocol for animal, and it's parameterized on the type parameter, which we'd call food, because we know that our meaning for that is food. And then if I wanted to say that cow was adopting this, I would do it by saying cow is adopting animal. What kind of animal? Okay, animals that eat grass. Right? That's how it could work. So why doesn't it work this way? And this part's a bit subtle, but I think the answer has to do with the way that the type alias style definition of an associated type, as opposed to the generic parameter style definition of associated type exposes that type. From the outside of the protocol, let's say we did have generic protocols in this way, and you were consuming it. The only way you could sort of see the associated type in order to declare constraints on it or do other things with it is by parameterizing over it, right? If I wanted to feed an animal, I have to say feed animal A, it's type of animal O, but I also need to have the F in there, and the F appears on the feed animal signature. And then inside the implementation of feed animal, you'd be able to see F because it's one of the type parameters that you are parameterizing over for the definition of that generic function. But with a sort of Swift style pat, because the type alias acts more like a member of the type, you have direct named access to it. So I still need to parameterize over animal just because you always need to parameterize over a protocol with associated type. You can't just pass it in as a reference. That's something you can't get around. But once you're inside feed animal, you can directly figure out what that associated type is just by accessing it with normal dot-based access notation. And if you look at that notation, it sort of gives you a hint of what's going on here. The syntax that's being used means that the associated type is a lot more like a property of a type than it is like the generic parameter that was used to define a type. You're accessing it with a dot, and just like when I define a protocol and say you have to implement this function, you have to implement this variable, now we're also saying you also have to specify this type. And then that type is accessible. It's like one of the axes of customization that you're providing anytime you subclass something or anytime you implement a protocol. So that's a difference, but you might be looking at that and saying, well, that version on the top doesn't look so bad. Like, okay, my type parameter appears on the signature of things that are consuming the protocol. Is that so bad? Maybe it's not so bad for simple cases like this, but it turns out that this problem gets a lot worse when you're doing something heavier weight with it. So if you have many associated types, not just I eat this kind of food, but also I need to live in this kind of dwelling, and then I need to get this kind of drink, and then I need to be near this other kind of animal. If you have a whole bunch of associated types of the protocol, it gets more complicated. If the associated types themselves have associated types, and also if you're using a lot of protocols simultaneously. So when you add all of those things together, then the type constraint specification that you would need to put on consumers of these generic protocols gets very complicated because all of these factors are being exposed to the consumer of the protocol. They're not sort of embedded in the definition of the protocol. Now, I'd like to have a really tidy example here where I show you how it gets bad with the imaginary animal example in Swift. I started working on that, but I confess it gets complicated right away, and I think it's a bit more useful to just look at other examples from other languages of this. So here's an example of breadth-first search of a generic library for doing graph search, for doing a breadth-first search on a graph in Java version 1.3. Java version 1.3 actually had a problem like this. I don't know if they fixed it up in Java. I haven't been keeping track. But if you specify the command to start the breadth-first search on a generic graph library in Java, that is the type specification you see on the signature. What you're seeing there is a result of the fact that the type constraints involved in the associated types don't get embedded in the pat type structure. Instead, they're pushed out, and you have to interact with them from the outside and specify them and maintain these invariants from the outside. Whereas in contrast, if you do a similar implementation of a generic graph breadth-first search in C++, which ends up having better support for this kind of thing, the actual signature is much simpler. Here you can see there's only 3 type parameters instead of 1, 2, 3, 4, 5, 6, 7, instead of 8 type parameters, right? And you can see what's going on there in that traits declaration. There's a type name graph traits d vertex s. What that's saying is, okay, I'm generic over the class G, which is the type that defines the kind of graph I have, and from that type, I can get the associated type vertex that tells me the type of the vertex. So if I have a graph where every node is an integer, and I just tell you that this is the type that defines the graph, you can access the fact that that type requires that the types of the individual nodes as integers. You don't need to separately specify that. This is a functional programming conference, so I feel like we have to put Haskell on the board as well. So this is also old Haskell. This is compiled on Hugs 2002, but this is showing similarly, that you get this simpler syntax when you have this ability to embed information about the associated types. Now, why am I showing examples from 2002, 2003? The reason is I didn't come up with these examples myself. These were things that I encountered in the course of trying to understand the motivations behind the Swift design. And I think the magic key for understanding this more deeply is this document I found, which is a paper published finally in the Journal of Functional Programming in 2007, Extended Comparative Study of Language Support for Generics. And this reviews in detail the generic support in Haskell, Standard ML, Java 1.3 at the time, C#, C++, a language called Eiffel, and it implements a significant generic graph library in all of these languages. And then it looks at what are the problems. Like, oh, it was really easy to do in this language. It was hard to do in this language. It was okay in this language. And then based on that work, which is quite a few people working over a few years, this very systematic discussion of, well, okay, here's a generalized statement of the language features. And this language has these features, this language has these features, these ones are important for this reason. It's quite dense, but it's a great document. One of the outputs of it is this awesome table, where they have on the left a column that shows generic-oriented language features, and then languages, just seeing how they stack up. So multi-type concepts. That is protocols with associated types. So concept in C++ is a lot like protocol with associated type. Multi-type means that you can have multiple associated types. Multiple constraints, because you have lots of constraints on the types. At the moment, Swift lets you apply conformance constraints to the associated types. Maybe there's more coming. Associated type access, this is the thing I was getting at about how easily you can figure out what the associated type is. Constraints on associated types. Retroactive modeling, that means being able to apply an extension to a type that someone else defined or after it's been defined. Type aliases, sounds familiar. This was published finally in 2007, but if you go through and look at Swift, Swift ticks all the boxes, does a great job of it. Bravo, Swift team, bravo. And I don't think it's entirely a coincidence. I would be astonished if they had not read this. In fact, I think there's a lot of circumstantial evidence that they have. For instance, a lot of the terms that this paper invented to describe these features, it invented in order to describe them in a general way, because it was covering different languages. So some of these languages don't call them type aliases. Some of these languages don't call them associated types. But Swift does. It seemed a little bit like when they were thinking about how to define these language features in Swift, they sort of took this article, said like, great, this is how we do it. Why don't we just call them type aliases? Because it seems like we want to have those. I'm speculating, but there's something to this, I think. And also, if you look at the redoubtable Dave Abraham's talk, protocol-oriented programming, and look at the language he uses, there are times when the terminology he used shifts a little bit. So the language, which is not in the Swift programming language book, but is in this paper. So he talks about modeling a concept, which is something that's in this paper, although that's also the language that comes from the C++ world. And all the Swift guys are deep into C++, so maybe that's it. I think there's a lot of evidence that this paper is certainly insightful for Swift and may have had an influence on the thinking of the team that was working on the features. Another interesting table here is just describing how some of these different operations and procedures are named in the different languages. So you can sort of see how things map up, right? So, what they call a concept, or what would be, for instance, a type class in Haskell is most analogous to a protocol with associated type in Swift. The kind of refinement operation is one protocol inheriting from another, is what the SPL book calls it. Modeling, that's what we call adopting a protocol. Constraints are called constraints. So Swift fits in quite nicely. And I'm aware also when you look at some of this, some of the examples I showed, if you're coming from a more purely functional background, you might say like, well, Haskell actually has features that are like even better for this. And in fact, if you looked at this, you saw there were kind of asterisks here because even excellent Haskell support wasn't quite perfect, and developing this library exposed places where it was a bit awkward. And the reason that you might be thinking Haskell's great for some of these things is because actually this paper had a huge influence on Haskell. This article by Simon Peyton Jones and Chakravarti and Keller explicitly references the 2003 version of this paper and the difficulties that it exposed in handling certain kinds of scenarios with the Haskell type system, and proposed amendments that I think are now part of Haskell for handling these things. So it's all one. There's a small world, and people are paying attention to each other. Another relevant body of literature is the stuff around Scala. Scala is actually probably a closer analogy than any of these other languages mentioned, because Scala is this hybrid thing where functional aspects of it have been done in a very deliberate and functional friendly way, but it also needs to integrate with a pre-existing hierarchy OOP-based type system, the one that you get from the JVM. If Scala were a column here, I think you'd see what are called abstract type members in Scala are the closest analog to associated types in PATS in Swift. So that's a bit of a context on where it's coming from. Question number 3. Is this the plan? Really? Is this how it's going to be going forward? Or we're going to have to make everything generic in order to use protocols with associated types at all? Am I going to have to turn all my code generic just in order to deal with things that support equality? I think for the moment, yes, it does seem that way. Although, who knows what the future holds. I know that certainly around August of this year, before WWDC, there were blog posts where people were saying, I imagine they're going to fix this soon. This can't be the way it's going to be. But when the protocol-oriented programming talk came out, it really suggests that this is kind of the plan. So this is I think, the key slide from Dr. Abrams' talk on protocol-oriented programming. And here he kind of lays out the two worlds. And where he's calling one the without self-requirement and the with self-requirement, it's not just with self-requirement, it's with any associated type. And you can see right here the contrast, right? There's the contrast between dynamic dispatch, which is func sort in out a of array of orders, and static dispatch, which is func sort and then parameterizing over ordered things, because ordered is a pat, and then you have a array there, or there at the bottom, dynamic dispatch, static dispatch. Now, if you were a skeptic, you might say that some of the things on the right side were not great. Only usable as a generic constraint poses a lot of requirements on how you use it. All I wanted to do was equatable, but now I'm stuck with generics and static dispatch. Are these two worlds? Is this like the world of frustration? I don't think it needs to be that way, but I can understand why people are frustrated when they bump into this issue and don't understand the motivation behind it. And one thing I think that this slide doesn't represent is that the other world, where you don't have PATs, is not limited to those things. Maybe this is the world of choices. Like, yeah, you have the option of dynamic dispatch if you're not using a PAT, if you're using a plain protocol. But you can still do static dispatch as well if you're not using a protocol. So it's not like you're locked into dynamic dispatch on one side and you're locked into static dispatch on the other side. Actually, there's one side where you can do either, and then there's one side where you're stuck with static dispatch. You could use types as generic constraints if you wanted to on the non-PAT side of the protocol world. But based on this talk, you'd have the impression that this is the intended design of the language, and these restrictions around PATs are things we should learn to live with and embrace and appreciate. But I did put a little asterisk on that yes, and the asterisks represent existentials. Now, I haven't reviewed this material very deeply. In fact, Colin told me about it about 30 minutes ago, to be honest, which really embarrassed me because made me realize I should have gone into it more. But existentials is the name that you'll see in Haskell or the world of statically polymorphic, parametrically polymorphic languages that describe the kinds of the dynamic dispatch that you'd get in object-oriented languages. So basically, if you want to have a PAT and then have a reference to it, rather than have to use it as a generic constraint, what you would need for that is for Swift to support existentials. And are they coming? I don't know. We don't have anyone here from the Swift team to tell us the truth. But if you go and look inside the standard library, you do see some evidence that they regard this as a bug that don't exist yet. For instance, they have a fix me. So there's features in standard library right now that are described as, well, workaround for the inability to create existentials, and there's a radar for it. So maybe existentials are coming down the road, and in that case, it will be, a better world. In the meantime, there are workarounds that you can define, and indeed, you can see examples of them in the standard library. Types like any generator or any sequence are type erasing wrappers that you can define in order to work around the fact that the language doesn't define existentials. You can also define your own if you want. It's a somewhat irritating exercise, but it can be done. So for instance, I found myself building one for any interval. There's a protocol associated type of pat that defines the interval type, but that interval type has an associated type, which is the type of the scalar value that defines the intervals. So let's say you wanted to have an array of intervals where some of them were closed open intervals, and other were open intervals, other were closed intervals, an array of interval objects that represent all the possible values between 0 and 1. If you want to just sort of go through that array and check, if something is contained by any of them, well, you can't do that with a pat because it's a pat. You can only do these homogeneous arrays, so you need to create this type erasing wrapper just to have an array of interval objects. So it can be done. I could show that later if people are curious, but it's a bit of a nuisance. Maybe it'll become automatic if the language gave support for existentials. But again, I'd say, to understand is to forgive, and understanding why pats work the way they do gives us some perspective. So let me just review the 4 questions, hopefully to pull all this into some kind of shape. How are pats weird? I think the essence of it is that they lock you into generics and static dispatch, which maybe was not what you wanted. Maybe all you wanted was to be able to define equality. Type alias as a keyword specifically is a bit misleading because it does 2 very different things. One is handy, convenient syntax thing. Other is establishes a requirement on a protocol thing. And when you think about what an associated type is, I think it's as much like a required property as it is like a type parameter. So it's a good guide to have in the back of your mind. Again, why are pats weird? What's the motivation behind this? The fundamental motivation behind pats is to enable rich multi-type abstractions that don't fit into the pure hierarchy-like structure that you get with object-oriented programming. And why are they like properties of a type instead of generic parameters? It seems like this is a very deliberate choice to work around well-known and discussed issues in the literature where generic protocols don't scale well, and they don't really encapsulate the type invariance that they want to maintain in a nice way. That's where they're coming from. That's why they work the way they work. Now, are they functioning as planned? I think they seem to be, in that they're informed by a lot of research and a lot of comparison with other languages and similar language features. And if you look at all those languages are not as much oriented around dynamic dispatch as Swift is. I mean, C++ has virtual functions, but for the most part, the thinking that seems to have informed this feature is thinking that was focused on languages that were more static. I think that's where the staticness is coming from. I think the impact on a traditional object-oriented programming notion of a protocol is collateral damage. But maybe this isn't the end of the story. Maybe Swift's going to get existentials, and then we can be able to use pats in the way that we're familiar with using plain old protocols. Last question, right, was number 4. Like how to love them, how to embrace pats rather than calling them weird for half an hour. I think first step, call them pats. Makes them seem so much more friendly and familiar. They're just pats, right? They're not bad guys. They're just pats. Also, I think giving them a new name acknowledges that it's a new thing, right? Pats aren't the Swift version of protocols from Objective-C. They're actually a new thing that has new capabilities. You can do certain kinds of modeling of multi-type abstractions in a way that you simply couldn't have done before. It's not a broken version of an old thing. It's actually a new thing, deserves a new name, and that's a good way to think about why it also has new trade-offs. So call them pats, and if you're going to use them, then you need to embrace generics, at least at the moment, because they can only be used as generic constraints, so get comfy with that idea. If you still need dynamic dispatch, or if you need something like dynamic dispatch because of the purpose that you had in mind when you decided you wanted to use a protocol, I guess I only have 3 bits of advice to sort of end of the talk, so I can't go into it in detail. But one option is, instead of relying on dynamic dispatch, use enums and push the runtime variation into the value level. So instead of having a type and then 5 different subtypes and dynamic dispatch is picking the one you want, actually create an enum that has 5 different cases, and then inside it you could have an embedded switch, and that switches between the different values that you want. Maybe that's a better way to model your situation to begin with. The example I was working on with intervals for myself, I have like one solution with a type erasing wrapper, another with enums. This is workarounds. The other workaround, again, is the type erasing wrapper to hide dynamic dispatch inside a type. And this is what the standard library does when it would like to have a plain old protocol or an existential or whatever you want to call it. Also, if you still need dynamic dispatch, maybe wait a year and Swift 3. Whatever will come out, and then we'll have existentials, and then we can all just go back to our old ways. So that's my thinking on protocols with associate types and how they got that way. And when I started doing this, thinking about it, Apple was still a sort of black hole or opaque wall. And it was very hard to figure out what they were thinking, because you could sort of get hints of it on Twitter. But now, since the open source release, since the new sort of glasnost era of like open discussion about where Swift is going, maybe we can just ask them, and then we'll find out. It makes a lot of this detective work and criminology a bit unnecessary. So we can call them up later. I hope that explains this to some degree, and I'd be delighted to answer any questions.
Hi, that was a very interesting talk. Explained a lot of concepts for me. Can you elaborate a little bit on what makes these constraints? I'm not really familiar with that term being used in the context of a type being associated with the protocol. Like, is it just the fact that they introduce something that needs to be implemented, or?
So you mean the kind of basic constraint that they're under, if they can only be used as generic constraints?
Like, I guess, could you define constraint in this context?
Yeah, okay. So there's a few senses in which generic constraint is key to all this. But let me just focus on the most basic one at the very top, because I think that's what's puzzling about the error message the first time you see it. So if you look here, the error message you get when you try to create a variable that contains a protocol that uses self, or a protocol that uses some other associated type, like I'm doing here at this bottom line of this slide, the error that you get is this one. And the exact language is protocol, whatever it is that you're trying to put, can only be used as a generic constraint. Right? So let's like really break that down. What does it mean? The problem is that here, we're not using that protocol as a generic constraint. The protocol here called myEquatable is being used as the type of a variable, with the variable protovar. So what would it mean to use it as a generic constraint? It would mean this case here, right? So here, let's say I have my PAT protocol with an associated type or with a self requirement. It's called proto. And in this line here where I say 2, the only place the protocol appears is right next to the T. So when you see class is C, I'm defining a class. Here come my type parameters. This class is generic over T, meaning every different T I could put in there would produce a different kind of C, right? But, here comes the constraint part, I can't just put any T I want in there. I can't just put in an integer or a string or a whatever. It has to be a T that is a protocol, that can does adopt the proto protocol. So that's what it means to say that the PAT protocol can only be used as a generic constraint. I can't use it as the type of a variable or of a function argument or of a return value. I can only use it in this little bit of language where I'm saying, okay, here's a type parameter, but it's constrained. And the constraint is whatever type I fill in here needs to be a type that adopts this protocol. So that's sort of what it means. Does that answer the question? I feel like this is the essence of it. And it's very puzzling if you haven't done a lot of generic stuff before.
It's actually more a follow-up comment, but when I first tried to understand it, it was very helpful for me to understand that when you have the type alias and you try to use the protocol that you're actually working with an unfinished type. There's still like holes in the type definition that are going to be filled by the class or struct that implements the protocol. By using that generic constraint, you basically define who's going to implement it and who's going to fill the holes and then fulfill the final type specification, essentially.
That's a useful insight. And when I first had that thought, that's what led me to thinking that everything could be understood by just regarding protocols as PATs as generic protocols, right? Because you can't have an array of different specializations of the same generic type. Like I couldn't have an array that had the first element being itself a array of int, and the second element being a array of string. The array of int and array of string are different types. You can't have an array that contains different types. But when I first started thinking about this, I thought like, oh, maybe the reason I can't have an array of PATs is because they could all be different under the hood. But that's not actually the essence of it, right? Because if that were the only problem, if that were the only issue, that a PAT is a kind of a generic, and so they're actually diverse types, if that were the only issue, that would explain why you couldn't have an array of PATs that were differently specialized, but that wouldn't explain why you can't have a uniform array of PATs. And it wouldn't explain why you can't have a single variable that's a PAT, right? Because you could, because then there's no ambiguity. Then like you have a specifically defined PAT that's adopting with a specific knowable associated type. So I think it's very useful to think about in the sense that typealias defines a requirement that needs to be met, and it's an unfinished type until that's met. But that's not the fundamental reason why you can't use them as variables. The fundamental reason you can't use them as variables is that right now they've only built the machinery for static dispatch. And it seems like they want to build the machinery for dynamic dispatch as a thing on top of it, existentials, whatever, rather than the way people had done for OOP learning. I hope that's helpful. Yeah, but that insight is what led me to think about, oh, maybe it's just because they're generic protocols, but I don't think that's all there is to it.
So I found myself in the same situation as you mentioned. I ended up with the solution of using enums. However, at the end, I wanted something to be a little bit easier to use, so I created a bind. And when I did the bind, because the bind is declared generically, I found myself back to square one, and I couldn't use it again without making binds specific again. How do you deal with that? How do you deal with, you just have to do that switch statement again and again and again?
Yeah, I don't know. But it's a problem. So both of these workarounds of pushing the dynamic dispatch-like behavior into enums or pushing them into a type erasing wrapper involve a lot of boilerplate. Because, like, let's say I have a plain old protocol or even a superclass that has 100 functions, right? And then I create different subclasses of them. And then you get dynamic dispatch on all of those functions. Whereas if you're using enums or if you're using type erasing wrappers, I think you end up needing to create like 100 switch statements. I'm not sure about that, but that's been my experience so far. There might be some clever pattern in there, but I haven't found it. So it's a pain in the butt at the moment.
Thanks a lot for your talk. That was really great. Definitely learned a lot of stuff about PATs. A lot of the programmers that I admire and follow on Twitter reference academic papers like the one that you brought up during your talk. So my question is, where did you find that paper? How did you discover it? And also, is there like a cool website or resource that I could use to find papers that touch on my interests? Sorry if that's a tangential question to talk about.
Fine. I was writing a book. I was writing a chapter of a book, the functional programming chapter and the generics chapter of a book on introductory programming in Swift. And when I agreed to write that, it was because I didn't really understand generics. I thought, well, if I write a chapter on it, that'll force me to understand it really well. So I just was Googling a lot on generics and trying to understand them in comparison with other languages. And I was also studying Haskell at the time, so I'd like run into these issues. And I think just Googling on generics, I eventually stumbled into a reference to this paper. But then I found an old preprint version of it. And one of the things just as a kind of practical matter, when you find academic papers, they're usually locked up behind some paywall. But then if you look at the names of the authors and go to that author's website, then they usually distribute the PDF for free or a PDF in early version. And then if you decide it's worth it, you can flunk out the $50 to buy the official version. So I just sort of Googled around and then a bit of detective work to chase it down. But I thought this paper was really good. I mean, we have a community where we talk about technology issues, and there's kind of blogs and talks. And the academic community is more separate from that than it should be. But this paper is fantastic. This is like 4 or 5 people working on this over years with NSF funding, systematically developing different graph libraries. It's like a lot more work and thought went into this than putting together a blog post. And really, I'm just trying to communicate a little fraction of it. So I think it's really worth digging into these papers just whenever you bump into them.
Thanks a lot.
Let's do one more question on the other side. Maybe one other good place to find papers is Lambda the Ultimate. This website.
Yeah, that's a good one.
Yeah. Lambda the Ultimate, like Lambda as in Lambda function.
Yeah, there's a website for programming language stuff.
This is just a quick comment. 6 days ago, there was a proposal on Swift Evolution that was merged into Swift 3 that will hopefully alleviate some of the ambiguity around the typealias keyword. It's going to now use associated inside protocols, and in Swift 2.2, they'll deprecate the use of the typealias keyword inside protocol definition. So,
I like that. Yeah, I'd heard about that, but
so the reason I'm bringing it up is part of the excitement around Swift being open source is that we can now witness and participate in precisely that evolution. So thank you for your presentation.
Thanks. Yeah, I think that's a good development.
Question.
Yeah, sure.
There's one at the back. Getting my exercise point.
Hey, awesome talk. I learned a lot. Could you go into the definition of type erasure? I'm not really familiar with it, and kind of maybe go into the any generator or any sequence example, like how that's an example of type erasure.
I think I'd do a better job showing the example I worked through than trying to provide a definition in the abstract. But let me go through the example. Maybe not right now because there's other questions, but later, and then that can sort of show it. I think I have a hard time putting it in language well, but basically you have a type that is concealing the fact that there were parameterized types underneath internally. So from the outside, so for instance, like let's say I have any sequence, right? So that's an example of a type erasing wrapper that's in the standard library. If I had some type which was a sequence type, then it would be a sequence type of some particular element type, right? So let's say I have a sequence, let's say I have a type which is a sequence type of integers. Now that type has 2 types associated with it, right? Well, integers, obviously, we know it's a sequence type of integers, but we don't just know that it's a sequence type of integers, it's a particular type, right? It could be an array of integers, or it could be some kind of linked list of integers. So there's 2 types that you're managing in that situation. You're managing the element type, what it's a sequence of, and then you're actually managing the type of sequence type it is. Is it an array or is it a linked list? You might have situations where what you wanted was just to have something and know that it have a type that just represented a sequence, like any type at all that represents a sequence of integers, and you don't actually care if it's an array or if it's a linked list or whatever. So you can create a type, and that's the type erasing wrapper type, which kind of disguises if it's an array underneath or if it's a linked list underneath, and it only exposes that it's giving you an interface, a sequence-like interface to integers. So that's an example of a type erasing wrapper that's in the standard library. So I'm not sure how to define that abstractly, but that's what it is. And if you wanted to get something like dynamic dispatch, you'd need that, because if you want dynamic dispatch, then maybe you don't care about some type fact underneath. You just want to be able to know that you can call a method. And so that means, so if you get a type erasing wrapper, then you don't need to use the type as a generic constraint because you know that you have in any sequence. Is that a bit helpful? I can walk through an example later, but that's the gist of it.
Okay, let's do a final question and then lunch and talks. Yeah.
You showed the slide from Dave Abraham's talk on protocol-oriented programming, and I feel like that's a very helpful distinction between the 2 types. I guess as more a comment on the motivation, it seems like in this case, and if you look at what Swift is, like it's very much like a bridge between 2 ecosystems, one of which we don't really know what the other end is, like whatever Cocoa in Swift looks like. Like the AppKit and UIKit are very much designed around like dynamic dispatch and Objective-C. So like, do you think this is more of a scaffolding on the left side? The ones without the self requirement, that's more of a scaffolding that's not for the sake of static type information, but really just like until they have a nicer method to do dynamic dispatch.
I don't know. I think one question is, let's say you got existentials. Then you wouldn't have this static dispatch on the right-hand side as the only way to do it. Would that give you functionally all the same things that you get from left-hand side? I don't know.
I don't think it would give you everything, but I think
it would give you a big piece of what.
Yeah.
So yeah, I don't know. That's the interesting question. So when I first started looking through this, and especially looking at the thinking that seemed to inform this, I would have thought that this would be true a year and a half from now.
Yeah.
Just that stuff that existentials and it being marked as a fixed will be better.
Cool. Well, let's thank Alexis again. So there will be lunch. Maybe it's not there yet. It will be there within minutes. A conference is not only about listening